So this video is going to go over sigma and pi notation. You'll probably find when you go to university that it is assumed that you know how to use these and know how they work, and you won't really go over them that much. So this is just a video to give you the basics. So starting with this symbol here, this is sigma, and you can pretty much think of it as meaning the sum. So here is a typical sigma expression. And this reads as the sum between I equals 1 to 5 of 1 plus I squared. So the letter below the sigma sign, so in our case I equals 1, is known as the index of the sum. So it can be any letter, not necessarily I. And what you do is you first start with substituting this number here into the equation. So using I equals 1, clearly this is going to be 1 plus 1 squared. And then what you do is you then substitute I equals 2 into the equation, so add 1 to your previous term, and you add them together. So 1 plus 2 squared. And you do that all the way from 1 to your top number here, which in our case is 5, adding them all together on the way. So plus, when I equals 3, this will be 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared. Now, as you may have noticed, it doesn't matter, the brackets don't matter in this because you can add the numbers in any order and you will still get the right answer. So this is the same as writing 1 plus 1 plus 1 plus 1 plus 1. So that's taking the first term out of all of these brackets, and then plus 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is the second term in all of these brackets. So as you may have noticed, this is the same as writing the sum between I equals 1 to 5 of 1, as you go from 1 to 5 and each term is just 1, so there's no I component in this one here, plus the sum between I equals 1 to 5 of I squared, which is this part here. So you can see that that's true, as substituting I in for each one is substituting 1 squared, 2 is 2 squared, and so on and so forth. So this works for any finite sum. So a finite sum just means a sum where you add a non-infinite amount of numbers. So infinite sums are defined, but they have a few different rules, so we'll stick to finite for now. So here is another example of sigma notation. So if we go through this again, starting from I equals 0, clearly any number x to the power of 0 will always be 1. And then next, taking I equals 1, clearly x to the power of 1 is always going to be x. And then I equals 2 will be x squared. And this goes all the way up to x to the power of n. So this is a bit different to the last question, as we won't get a definite answer, a definite quantitative answer, as we have an unknown number of terms and this unknown number x. So you have likely seen this equation here before. It's the geometric series with first term 1. It has a common ratio of x, so as you can see, every term you multiply it by x to get the next term, and it has n plus 1 terms. So a very common mistake is thinking that there are only n terms, but as I equals 0, clearly there will be n plus 1. So using the usual result for a geometric series, we know that this equals x to the power of n plus 1 minus 1 all over x minus 1. So if you're worried about how we got to this here, don't be. It is something that you just have to learn. So if you do learn it, it will come in very useful throughout university. So this is a bit of a harder summation question where it has more than one index. So we have two indices, I and j. You apply the same logic, but you have to run the equation over all possible outcomes of I and j. So clearly, as we have three possible numbers for I and three possible numbers for j, there are 9 possible combinations of I and j. So what you do is you run the equation for all of these 9 combinations and take the sum of all of them. So if you feel like you can do that just by yourself, go ahead and pause the video. If you need a bit of help, I'll run through it quickly now. So starting with our first combination, let's take I equals 1 and j equals 1. So then ij will be 1 plus I, which is 1, plus 1. So that's our first term. Next, if we take I to be 1 and j to be 2, then ij will be 2 plus 1 plus 1. And then next, taking I to be 1 again, but j to be 3, we will get 3 plus 1 plus 1. And then if we take I equals 2 and j equals 1, we'll get 2 plus 2 plus 1. And then taking I to be 2 and j to be 2, we get 4 plus 2 plus 1. And then again taking I to be 2 and j to be 3, we get 6 plus 2 plus 1. Now if we take I to be 3 and j to be 1, we get 3 plus 3 plus 1. If we take I to be 3 and j to be 2, we get 6 plus 3 plus 1. And finally, when I equals 3 and j equals 3, we get 9 plus 3 plus 1. So the sum of all of these numbers together equals 63. So this is a more general form of a summation with two indices. So this here just means any function of some variables I and j. So our last example also was a function of I and j. I'm running it from I and j equals 0, I equals n, and j equals m. Notice how they can have different ending points. Now this can seem really daunting at first, but if you break it down, it becomes a bit more manageable. So for example, if we set our j as to be 0, and then we can run the equation from I equals 0 to n. So that would just be, oh, I'm on the rubber. That would just be the summation from I equals 0 to n, as we've set our j equals 0, of f I 0. And then we need to set our j equals 1. So this whole process is to make sure that we have every possible combination of I and j. So next, if we set our j equal to 1, and again run I from 0 to n, that would be the sum between I equals 0 and n of f of I1. And we can do that for every single j. So just changing this part here, so 0, 1, 2, all the way up to m. So plus dot 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 plus the sum between I equals 0 and n of f I m. So as you can see, the only thing that changes in each of these equations is this part here. Otherwise, they are all the same. So this can be split into two summations. So as all the sum of these will be running through j equals 0, which is our first term here, all the way to m, of the summation of I equals 0 to n of f of I j. So that just simply means that you start with this summation here, and so starting with j equals 0, and then you run all of this from I equals 0 to n, and then you move on to j equals 1, and again run all of this from I equals 0 to n. So if you break it down into two different summations, you don't get confused about the possible outcomes, and it makes it a lot more manageable. So this here is an even more complicated question. But again, if you break it down, it is not that hard as long as you do it in simple steps. It's easy to get to the answer. If you feel like you can do this yourself, again, feel free to pause the video, but if not, I will go through it now. So if we start with I equals 1, clearly this equation here will be running 1 plus j from j equals 1 to 1. So when I equals 1, this will just be 1 plus 1, and as we're only running to I, which is 1, we stop there. Next, taking I equals 2, this equation here will be 2 plus j from j equals 1 to 2. So starting with j equals 1, I equals 2, so that will be 2 plus 1. And then our next term will be when j equals 2, so that will be 2 plus 2. And then we stop as our top number here is I, which is 2. And then finally, our last number for I is I equals 3, and that is running 3 plus j from j equals 1 to 3. So starting with j equals 1, that'll be 3 plus 1, and then j equals 2 will give us 3 plus 2. And then finally, as our top number here is 3, we stop at this one, which is 3 plus 3. And adding all of these together gives you 24. So this is everything I'm going to go through for the sigma notation. I'll move on to pi now. There is obviously more to cover, but this is just the basics of sigma and how to use it, so that when you're at university, you don't feel behind. And I'm sure the more complex stuff will be taught to you throughout your degree. So now moving on to pi notation. This symbol here is actually a capital pi, not the lowercase pi. The number pi that I'm sure you all know and love actually has nothing to do with the capital pi in this context. So using this capital pi is really similar to sigma, but you take the product instead of the sum. So if I go straight in and draw an example, this equation here, this is the product between I equals 3 and 6 of I. So doing the exact same as we did with sigma, we start with our index number here, which is 3, and then add 3, 3 add 1 is 4, so substitute that in here, but instead of adding, because it's a product, we are timesing. It's times 4, and then all the way up to your top number here, which is 6. And this equals 360. So really basic. You will probably find that this is a lot easier than sigma notation, as it's a lot easier to factorize. So here is another example, really similar to the last one, but this is just to show you how to factorize out a scalar. So as multiplication is commutative, that means it doesn't matter which order you do it in, the outcome will always be the same. This, can be split into two parts. So it can be the product between I equals 3 to 6 of 2 times by the product between I equals 3 and 6 of I. Now, as this here doesn't contain an I component, this means that it will always be 2. So as we run it 4 times, for 3, 4, 5 and 6, this part here will simply be 2 to the power of 4 times by this here. Which is simply 16 times by what we found in the last part to be 360, and that equals 5,760. So similar to sigma notation, with pi notation, you can have multiple indices, but I'm not going to go through that now as I feel like we covered all of it with sigma. Again, this is just the basics. It can get more complicated, but you will learn that at university. So feel free to go ahead and take one of the mini tests on our website, or if you feel like you need to go over something, you can rewind the video or just take a break.